So now let's take a look at question 1. For question 1 here we have 8 small questions, and I think the first 4 questions are easier than the rest of the 4. So I will just briefly explain the first 4 and put more time in the rest of the 4. Okay, so use L'Hopital rule to evaluate the following limits. For some of the limits here, we've already known how to solve them from the course Math 1500, and now we just want to use a new method to solve it to kind of do it in another way. Oh, I've already had it here. So, yes, question A. If we want to use the L'Hopital rule, we must make sure that the limit is of some type. It's either 0 over 0 type or the infinity over infinity type. Otherwise, we are not allowed to use the L'Hopital rule randomly. So the first step is to indicate that the limit of the numerator and the limit of the denominator is equal to 0, right? So when you substitute this into 2 into the numerator, you see that the numerator goes to 0 and the denominator also goes to 0, right? So this is equal to it's a 0 over 0 type, right? And we are allowed to use the L'Hopital rule, right? So it's equal to limit x goes to 2, and I can replace the top by the derivative of the numerator, which is the derivative of this guy, which is square root of 2, and the derivative of the denominator in the bottom, so that is 2x minus 3. Now I try to evaluate this limit. It's a relatively easier, simpler expression. I can substitute 2 into it, right? So it's square root of 2 divided by 4 minus 3, which is square root of 2. Very simple. Oh, actually, I did a mistake here. I didn't see that this square root of 2 is, this square root is like, the x is also underneath the square root. So let me make a little bit adjustment here. So the derivative for the numerator should be square root of 2 multiplied with 1 over 2 square root of x. Okay, so do this adjustment. Sorry for the carelessness, and then that is cancel out, right? So it's 1 over 2, not square root of 2, and this is the answer. Okay, so if I'm making any mistake here, just correct me, thank you. And now let's take a look at question B. Question B, so x goes to the infinity. Let me just copy and paste this here. And we know that both the top and the bottom are going to infinity, right? If x is going to infinity. So this type of limit is of infinity over infinity type, right? And now we are allowed to use the L'Hopital rule. So by doing that, I can write this as x goes to infinity, but now I replace the numerator by the derivative of the numerator, which is 4x minus 1 divided by this kind of, what is this? Negative, is it negative? Negative 6x plus 2, right? And still, if we want to solve it, you see that the numerator and the denominator are still going to both going to infinity. So now it's still of this type, so I am allowed to use the L'Hopital rule again, right? So this LR applies again, and I can write this as excuse me, this limit x goes to infinity, and the top is replaced by the derivative of the original expression, that is 4, and this is -6, and then this is a constant, right? So it's equal to negative 4/6, which is -2/3. Very simple, right? Just take the derivative directly every single time. But before doing so, we make sure that both the bottom and the top are going to infinity. That's the various first assumption that allows us to use the L'Hopital rule. Okay, so that is question A and question B. Question C here. This limit is obviously does not exist. It has nothing to do with the L'Hopital rule. If you want to apply the L'Hopital rule for it, you see that it's not allowed, because when you substitute -1 into the numerator as well as the denominator, none of them are going to 0 or going to infinity, so the L'Hopital rule does not apply here. But when you evaluate the left limit, right, this, the left, you see that the top is always 2, right? But when x goes to the left side of -1, x to the 3 is -1, right? So that is equal to 0 negative. So that is equal to -infinity. But when we evaluate this on the right side of -1, then this becomes 2/0 plus. That is because x to the 3 is a little bit larger than -1, so the sum of this x to the 3 evaluated at the little bit right side of that point, and 1 is greater than 0. So I'm not gonna do much on this, because we have already seen this on in the course 1500, and this is actually a very typical exam question in Math 1500, and you have passed the Math 1500, so I assume that you have known this, so I'm not gonna explain this question. So that is question C. And for now, question D here. I haven't wrote down the answer. This does not exist, the limit. Okay. So for question D, I have that. What do I have here? Limit x goes to pi. Right, so I need to substitute pi into the expression to see what I can get here. So substitute, and I see that this thing goes to 0, right? And limit cos 3 pi is the same as limit cos 3 pi is the same as cos pi, which is -1. So the bottom is also going to infinity, right? So it's 0/0 type. And for this reason, I'm allowed to use the L'Hopital rule. So now I can write limit x goes to pi. And the top now is replaced by the derivative of the top, which is 2 sine x times cos of x by the chain rule. And the bottom is, a negative sine of 3x times 3, right? And now I plug in the pi to evaluate this thing again, and I see that it's still going to 0, right? So it's 0/0 type again, and I'm allowed to use the L'Hopital rule again. Right, so it's equal to so so it's equal to 0 over 0 type LR, right? So it's equal to x goes to pi. Now I find the derivative of the top again, as well as the derivative of the But how do I do it? That's complicated. Oh, I noticed that I can actually simplify this expression by using the trig function identity. So this thing is actually sine 2x, right? So I can take the derivative of the sine of 2x. That's easier than taking the derivative of this product, right? So I have cos of 2x times 2 divided by negative 3 times cos of 3x times 3. Okay, so now I can plug in pi into this expression. Now I have cos of 2 pi, which is 1, right? So 2 here. At the bottom I have, cos 3 pi, that is negative 1, right? Negative 1 times negative 3, that's 3, so it's 9 here. So 2 over 9, that is the answer. Okay, so this is the trig function identity. I keep this in mind. If you're not familiar with it, look up the formula in the textbook. Now let's take a look at the rest of the 4 questions. So there are more, I think much more difficult. So first, this question E. So this question E, we will need to rewrite it as a fraction because we want to use the L'Hopital rule. We need a fraction type. So that is limit x goes to infinity. There's x squared divided by 2 to the x, right? Because this thing is written as 1 over 2 over 2 to the x now. Now it's of the fraction type. I can plug in infinity, right? And see both the top and the bottom are going to infinity. So it's infinity over infinity type. I'm allowed to use the L'Hopital rule for this reason. So I take the derivative of the top and the bottom. I have 2x divided by 2 to the x times ln 2. Right? And now I plug in infinity to this expression again and see that they're both going to infinity, still going to infinity, which means that I apply this again, take the derivative of the top and the bottom again, and now this becomes 2, and the derivative of the bottom is 2 to the x times ln 2 times another ln 2, right? And now only the bottom is going to infinity, the top is already a constant, so we see that is 2 over the infinity, which is equal to 0. And therefore the limit is 0 for this question. Now the next one here. Next one here. We need to rewrite it, so that is a fraction type. So I have this 2 over x minus this cotangent, which can be written as cos x over sine of x. And then I combine these two fractions by choosing a common denominator. So for the first fraction can be written as, or you can say cross multiply these things. So this is 2 times sine of x, cross multiply, and this is x times cos x, right? So it's a fraction right now, and I plug in 0, and I see that both the top and the bottom are going to infinity, going to 0. So this is a 0 over 0 type, and the LR applies, so I can write this as the derivative of the top, which is 2 cos x, minus, now this is difficult, the product rule, right? So that is this 1 times negative sine of x, 1 times cos of x, plus x times negative sine of x, divided by the derivative of the bottom, that's also product rule, so x times cos of x, minus plus 1 times sine of x. And then I simplify this a little bit, so I have limit x goes to 0 plus, this is cos of x, right, minus, that's plus, that's x sine of x, x cos of x plus sine of x. And now I plug in 0, right? Plug in 0, and I see that the top is going to 1, right? And the bottom is going to 0, but it's positive 0. By writing positive 0, I mean it's a little bit larger than the number 0. It's a very, very small positive number, because we can judge from the graph that when x is approaching 0 from the right side, sine x, cos of x, and x, they're all positive numbers. So this is 1 over 0 plus positive infinity. So that is the answer of question F. Now let's work on this G, which is crazy question. Very difficult question. So we have this limit, x goes to infinity, ln of x to the 1 over x raised to this power. So whenever we encounter this, you will be likely need to use the log function to help you. So I will let here y equal to ln x to the, right, and then we take the ln on both sides. So ln y is equal to ln of ln x to the over x, which is equal to 1 over x times ln x. So it's double ln here. Okay. Now our goal is to find limit x goes to infinity of this expression. So that is limit x goes to infinity of y, right? And this can be written as x goes to infinity e to the ln y And then we know we are also allowed to move the infinity sign to the top in the exponent. So this is equal to e to the ln y. Right. So now the goal is very obvious here. We want to find the limit of ln of y, because finding the limit of y is difficult, so we want to find limit of ln of y instead. And after we found it, we substitute this back into the exponent of this this exponential function, this e functions. So that is the goal. We're doing it indirectly. Now we have the expression ln y equal to this, right? So what is the limit of ln y? So let's find the limit of ln y. That is equal to this fraction, right? We like fractions because we can use the L'Hopital rule, right? So now the top is going to infinity, bottom is also going to infinity, because ln x is going to infinity, right? So if ln x composed with another ln is also going to infinity. So it's infinity over infinity type. So the LR applies. Now I can write this as derivative of the top, that is 1 over ln of x, times the derivative of the inside, that is 1 over x, divided by 1. Right? And it's obvious that this is 1 over infinity times 1 over infinity. So it's 0. So now we have the limit of ln y equal to 0. Right? So this is equal to e to the 0, which is 1. See that? Whenever we have difficulty finding the limit of this expression, we take we set this to y and take the ln on both sides and kind of do this indirectly. So that is the answer of question G. So now let's take a look at the last question. So this expression is difficult, so we let this equal to y, x equal to y. Now take the derivative, take the ln. So we have ln y equal to ln of this x to the ln this. Therefore I have ln 1 minus x times ln x. Right? And then this is limit x goes to 1 minus y, right? Then I can write this as limit goes to 1 minus e to the ln y. And now move the limit to the top, to the exponent. And now we're going to find the limit of ln y instead. So what is limit of ln? Of ln y? It is limit of this expression. And again, we know that we want a fraction. We don't want something like this. We want something where we are allowed to apply the L'Hopital rule. So we're kind of rewriting it. So it becomes ln 1 over x divided by the reciprocal of ln x. Now it's a fraction, technically. Right? But in order to apply the L'Hopital rule, we need to make sure that this fraction, its limit is of some type. So when we plug in 1 into the numerator, we see that it's ln 0, so it's infinity, right? And when we plug in the 1 in the denominator, that is 1 over ln 0, or ln negative 1, ln 1, ln 1 is 0. And 1 over 0, that is also infinity. So this is the infinity over infinity type. And we're allowed to use the LR for this reason. So now I can start to take the derivative on top. That is 1 over 1 minus x times negative 1. And the bottom, that is just negative ln x bracket square times 1 over x by the chain rule. Okay, now I can plug in. Can I plug in? So if I plug in, I will have something 0 in the numerator, right? So I may want to, simplify this a little bit before I do so, because you simplify this. So this simplifies to, I can cancel out the negative ones, right? And I flip this ln square on the to the top. So I have ln square x here divided by this 1 minus x in the bottom, and I'm also flipping x to the top. So it's like that. Right. Now I plug in 1 into the expression, and I see that the top and the bottom are still going to 0. So again, we apply the L'Hopital rule for this reason, this 0 over 0 type. Now I take the derivative again. So now it becomes x times 2 ln of x times 1 over x by the chain rule and the product rule. This is just ln square of x, and the bottom has already become negative 1. Right. Now evaluate this, plug in 1 in this expression. When I plug in 1, this factor is 0, right? This factor is also 0, right? So the answer is 0. Right? And I haven't finished, right? This is just the limit of ln y. We need to also plug in the 0 in this expression, so it's e to the 0, which is equal to 1. Right? So that is the answer of this question. It's equal to 1. That is question H. Now let's take a look at question 2. Use the left point approximation with 6 subintervals to approximate the area under the curve fx equal to square root of x from x equal to 1 to x equal to 4. Sketch the curve, the graph, and the rectangle, and use this to determine whether your estimation is a underestimation or overestimation. So firstly, kind of grab this. So this is the y equal to square root of x, something like this. And we are starting from 1 and finishing at 4. So assume that this is 2, right? This is 3, this is 4, right? And now we have this 3 intervals, and then we need to subdivide them into smaller intervals since we want to have 6 intervals, right? So the length of the total interval is 4 minus 1, that is 3, divided by the number of intervals 6, right? So this 4 minus 1 divided by 6 is equal to 1 over 2. So you see that the length of each small interval is 1/2. So I'm building this here. 1/2. And then second interval, starting from this 1/2. Okay. The third interval. Okay. Third interval is too large. Finishing at 2.5. Right. And continue. You can imagine how you can build it, build them. Okay. Something like this. Okay, so we have 6 small intervals, and this question also says that you need to use the left endpoint, right? And you see that I'm using the left endpoint to determine the height of the intervals of the rectangles, right? So this is the approximation. It looks like this. This is x. Now, I want to approximate its area, and let me write this formally. We've got the right endpoint, the left endpoint, a equal to 1, the right endpoint b equal to 4, right? And the delta x length of the interval is b minus a divided by 6. That's the number of the intervals. 4 minus 1 divided by 6, that is 1 over 2, right? So we have the xi equal to the first endpoint, a plus I times delta x by the formula, which is 1 plus I over 2, okay? Choosing the left endpoint because of that. And now the area A by the formula can be approximated as, so it's approximately equal to sigma I from 1 to 6. This f of x I minus 1 times delta of x. I'm using I minus 1 is because I'm using the left endpoint, and it does not have to be I minus 1. If you let the index equal to starts from 0, then you can write this as f of xi. So it has something to do with the way you write the index, right? So if you write sigma I from 0 to 5, then it's f of xi instead of xi minus 1. And anyway, you can check whether you're starting at this number 1 here, right? So you want to start at this number 1, that is the left endpoint of the first subinterval. So that is when I equal to 0. So you want this I equal to 0, the subscript, right? And the index here is starting at 1. So you need this xi minus 1 in this expression so that it can start from 0. Okay, just imagine this. Now that's equal to sigma 1 equal to 1 to 6 of this expression. Just substitute everything into the function I minus 1 divided by 2 times 1 over 2. Right? Okay, 1 over 2 is from the outside. One over 2 is the length of the interval. Right? So this thing is the xi minus 1. Okay. Now you can just write this out by substituting I into this expression. So it's a little bit tedious to do. Right? So it's 1 times 1 half plus this 3 over 2 times 1 over 2 if you substitute I equal to 2 in this expression. And if you substitute 3, then you will get 5 over 2 times 1 over 2 here. And plus, oh sorry, I should remove this sigma when I substitute this. And plus this square root of 3 times 1 over 2 and plus 7 over 2 times 1 over 2. So see if I'm missing any terms here. Oh, I'm missing one term. That is the square root of 2 times 1 over 2. Okay, so totally I have 6 terms here. 1, 2, 3, 4, 5, 6. And they're obtained by substituting I equal to 1, 2, 3, 4, 5, 6 in this expression. And sum them up, that's equal to what is the answer? So equal to something anyway. I forgot the answer. You can sum them up and see the answer. Just say arithmetic. So that is our question 2. Now let's see question 3. Express the area under the curve by using a limit. So same stuff. We take a look at the interval first. It's from 2 pi to 3 pi. So you see that A is equal to 2 pi and B is equal to 3 pi. Right? Now the length of the interval, each small interval, delta x, is equal to b minus a divided by the number of the intervals. And since we are using a limit, so we need infinitely many intervals. So the number of the subintervals will be equal to n, and n is gonna go to infinity after. So this is b minus a equal to divided by n, so it's pi divided by n. Okay. And now we also want xi. Right? Xi is equal to this a plus m n I times delta x, which is 2 pi plus this I times pi divided by n. Okay. Now you can write out the area of A by using the approximation sigma. Now n goes to infinity. Sorry, sigma. Limit n goes to infinity. of this summation I equal to 1 from 1 to n f of xi times delta xi. Just the formula. Now I substitute everything into this expression. So I have f of xi. I have my xi here, right? My f of x is here. So that is this 2 pi plus I times pi over n. This thing times sine of 2 pi plus I pi over n. Right? And at last I need a time times the length of the interval, that is pi over n, that's delta x. Right? And maybe you can simplify this a little bit by removing the 2 pi, since that is the period of sine of x. But you don't have to, because you have expressed the area under this curve by using a limit, and that is all you have to do. So it's done here. So that is the answer of the question 3. So a little summary of this tutorial. We have used the L'Hopital rule to solve various type of limits. Some of them are easy, just take the derivative. And some of them are difficult. We sometimes need to make use of the log function to help. And sometimes we also need to derive the function many times until we no longer have, until we don't have the 0 over 0 or the infinity over infinity type. And it takes experience and practice. So that is question 1. For question 2 and question 3, we are basically just using definition. As long as you're familiar with how the integral is related to the limits, you can play with them. Make sure you know the left endpoint and right endpoints and the formulas and how to build those small rectangles. So that's basically what it is.